I guess we'll get started. Hello, everyone, and welcome to this final session of the pre-day for financial services. This is a hardy bunch. Showed up at 5 o'clock. Great job, you guys. Awesome audience. I know I'm between now and the happy hour, so we'll try to keep it as light as possible. And if you guys know of any good parties later, reach out to me. Reach out to me, and we'll try to make some action happen. So anyway, the talk that I'm giving right now is about grid computing for risk management on AWS. I am Pawan Agnihotri, Principal Solution Architect at AWS for the global financial services. And I've been with AWS for about 3.5 years, worked in the financial industry for 13 plus years before that, and have deep knowledge of work primarily in the HPC space, big data platforms, machine learning, security, and networking. So to get started, grid computing is one of the most frequently asked solutions in our discussions with financial services. Financial services run some of the largest grids for risk management. In this session, I'm going to cover the solution that I have built, working with some of the customers to develop large-scale grid environments on AWS. By the way, how many of you are running grids today on premises, by the show of hands? Quite a few. Keep your hands up. I have one more question to follow. How many of them are more than 10,000 cores? A lot of hands went down. 20,000 cores, still a few hands. 50,000 cores, still a few hands. Good, so this is amazing. In our discussions, we regularly see banks running 60 to 100,000 cores for risk management. I'm talking about the global financials. They regularly have risk calculations. And this is pretty important, right? Risk management is essential for the operation of the largest financial service institutions. The financial institutions need to stress test their portfolios to make sure that they are testing it against various scenarios, such as liquidity risk, credit risk, market risk, inflation risk, or just pure volatility in the market. The regulatory bodies are asking the FSIs to do more and more calculations. By FSI, it's a short form for financial services institutions, are asking the FSIs to do more and more deeper calculations to assess risk of their portfolios, to make sure that they have the adequate capital ratios. This is a very important aspect of the financial services. Their operation depends upon this. Apart from the regulatory requirements, some of these reports are required for the traders and senior management at the companies to make decisions based on what they have in their portfolios for next day's trading, right? What kind of risk they are holding. So they need to have those results. So not only is it a regulatory requirement, it's also a business requirement to have this for adequate risk and management of that risk within the financial services. There are many types of stress testing algorithms and models that customers use. CCAR, CCR, VAR. We have seen a new regulatory requirement come up. It's in the form of FRTB, which is a full fundamental review of the trading book. This has added additional complexity to the calculations required for risk management. In some cases, I've heard from our customers that the compute requirement is almost 3x to 5x more for running FRTB than they were using today. So all of these calculations require a large amount of compute resources. And banks have to invest in those grids because it is a required part of their business. So what is the problem here? Basically, there are multiple challenges when banks need to create these grids, right? As with any other infrastructure, there's a large upfront investment required for these grids. Like I said, if the banks are running 50,000 cores, 100,000 cores, they need to have that many servers. Along with that many servers, they need to have switches, routers, floor space to be able to house and run those servers. So it's a very capital-intensive upfront expenditure that the banks need to make. Limited floor space and capacity in data centers limit the size of the clusters that the banks can run, right? You don't have infinite space. So if you have a data center which is 10,000 square feet, maybe 100,000 square feet, you can only put that many servers in that square footage. So limited capacity leads to longer runtimes for your applications, longer runtimes for your risk calculations. In some cases, the banks have SLAs to meet to be able to report these values or results to various regulatory bodies. If you do not have capacity to be able to fulfill those requirements in a specific amount of time, there are fines. So that's another challenge that the banks have. Once you create a grid, basically you are stuck with it for 3 to 5 years. So if you chose an Intel platform, if you chose a specific processor, you have that standardized infrastructure in your grid on your premises for a long, long time. So you are limited in terms of what variations you can do with those calculations or the risk management calculation that you need, or model that you can run. If you need to change, for example, if you need to take advantage of maybe new libraries that have come out for GPU-based, you probably cannot use that if you don't have that infrastructure on-prem. So that's another challenge. Regulatory and market fluctuations require flexibility. Things like Brexit, US election results, these are all risk factors. They need tremendous amount of calculations, maybe on a short notice as well. So you need that capacity. You need that flexibility in your infrastructure to be able to support those various fluctuations that may be happening in the market. From a developing and testing point of view, there are production grids, and then there are developers who need to write code and test their code, develop new models. For example, FRTB coming out, they need to write code to do that analysis, to do that calculations. So they need parallel environments. Today, it's very difficult to get, if you already have one grid, it's very difficult to get a second grid for testing and development. Most of the customers I have dealt with, even that one grid that they have is shared between multiple lines of businesses. So that leads to backlog and inadequate calculations. So sometimes you have a failed job, right? So once you have a failed job, you don't have time to redo that job because you have a big backlog of processes running, already waiting from other lines of businesses to use that grid computing environment. So that's a challenge that we need to solve. When I talk to the customers, I often see this kind of a chart. The blue line that you see in the bottom is the chart that is shown by the departments, IT departments. That's basically showing the utilization of the grid. Generally, you have grid capacity, it's 100% utilized. It's a good thing to have a 100% utilized grid. But when you talk to the business, when you talk to the developers, they point out to the red lines. That's basically the number of jobs that they have in queue for processing that day, right? So even if the grid is 100% utilized, your business is not getting enough compute to be able to do their job. That impacts their schedules, that impacts their SLAs. A miss in an SLA for reporting to a federal agency could lead to millions of dollars in fines. A failed run on a particular day, you're done for. There's not enough capacity. Seeing the 100% utilization of your grid, there's not enough capacity to do it again. So what is needed for a solution? In a discussion with the banks, we need to be able to provide capacity on demand. So what that really means is when situations like Brexit happen, we need to be able to scale up the infrastructure. Also, we have seen the C-car calculations, the Monte Carlo simulations. These are basically a bunch of scenarios that are being run. So if you look at a normal risk calculation, there'll be multiple runs with multiple scenarios. Generally, one run takes 24 to 30 hours in terms of risk management calculations. You can actually reduce. So if you take the 6 runs, for example, 7 runs, 10 runs, you are actually talking in terms of months to achieve your risk calculations that need to be submitted for regulatory compliance. When you have capacity on demand, you can basically run parallel grids and parallelize your scenarios and runs. So each 30-hour run was run sequentially on your primary grid. Now, in the same 30 hours, by running 7 grids parallelly or 8 grids parallelly, you can reduce the amount of time it takes to generate those risk calculations. They need options to use different compute types. Developers today want to use the latest libraries, the latest feature sets available from the processors, maybe use graphics processors, CUDA programming to increase the speed of their calculations. So they need to have a flexible compute environment. Maybe some of the calculations are memory intensive. Maybe some of the calculations are more I/O intensive. Need to have different compute possibilities. In general, when you're doing risk calculations, you're going to be using a bunch of back data of your portfolios. You're going to have portfolio data. You're going to be having scenarios. When you run these, it generates intermediate calculations and then final results. All of these produce large amounts of data within the time of calculation as well as for steps before and after the calculation. For that, you need a large shared capacity that is available on all the nodes of your grid. So not only can you use the shared capacity for your code, but you can use the shared capacity for your calculations as well. And also that capacity needs to be very high performing because generally you will have calculations which are using a couple of kilobytes worth of data to do the calculations, and you'll be doing multiple millions of them in a Monte Carlo simulation, for example. So the storage needs to be high performant to be able to get and put the data from storage. And obviously, being a financial service institution, you have securities of the prime concern. So you need to be able to have a secure environment to run these grids. So talking about security, just want to mention AWS takes care of security off the cloud, right? So we run and manage our infrastructure. When we run and manage this infrastructure, we take care of all the security that goes along with it, right? From what we call the walls of the data center all the way up to the hypervisor. We run and operate our infrastructure at the highest level of security. And it's not only that we are saying it. Our infrastructure goes through regular certification and assurance programs. Every 6 months, we renew our certifications, we renew our compliance. We have achieved many of the compliances that are required for the infrastructure from all the regulatory bodies. So if you see some of the logos up here, FIPS, FINRA, FISMA, FedRAMP, SOC, these are all the same compliances that a financial institution will have to get for the grid that they run on-prem as well. This just makes the job easier for the financial institutions. Imagine a 70,000, 60,000 core grid cluster. You have to audit, log, track who put the patching cables, who moved the servers, what came up, what went down, what firewall rule changed, all of that, right? With AWS Compliance, you can just layer this as your infrastructure layer and build on top of this with your grid. AWS also provides a deep set of tools to help improve the security of your applications when they're running on the cloud, right? So we have services such as virtual private cloud, which allows you to cordon off your own private area within AWS. This gives you the flexibility to bring your own network definitions. So like if you are used to using a 10-dot network or 172-dot network, you can use a virtual private cloud to exactly bring that into your AWS environment. We have services such as key management service, which allow you to store keys for encryption, data at rest, data in transmit. There are very key and important requirements that banks ask us all the time about when they are transmitting data or moving data in and out of the cloud. So key management service allows you to encrypt the data and manage keys for the data. Identity and access management, IAM for short, allows you to provide fine-grained control over who can do what. Authentication, authorization on the cloud. Who can start resources, who can generate the grid, who can create the grid, how many grids can they create in parallel. All of those actions can be governed using IAM. And again, CloudTrail. It's one of the key services that I keep insisting whenever I speak to an FSI, always have CloudTrail enabled. It allows you to capture all the logs of audits that are required for many of the audit programs. So grids are all about performance. Without performance, you're just going to waste your resources. Developers want to utilize the fastest and the best options available to speed up their calculations. So this has many dimensions. One of the dimensions of performance is compute capacity. AWS runs the cloud in over 14 geographic regions around the world. So data residency, if you have a data residency requirement for a specific calculation, you can use the region which is in the area that you need data residency about data residency. Within these regions, we have what we call availability zones. We run about 38 availability zones, and an availability zone is basically one or more data centers. So the graphic I've thrown up there, which shows you that we run data centers which typically have about 50,000 servers, could be up to 80,000 servers. So that's the kind of capacity that we have in a single data center. In each region, we have 2 or more availability zones. So the amount of data centers or amount of capacity we have is good enough to run the largest of the grids. Another factor in performance is networks. A lot of these small calculations of Monte Carlo, they push and pull small amounts of data, 2 kilobytes, and they use schedulers to execute the jobs on the various compute nodes. To be able to efficiently use your compute resources, you need to have the network which is able to support the throughput. AWS runs a proprietary 10 gig network, which provides you with full bisectional bandwidth in placement groups. And what that means is basically it's a sort of a mesh network. It's not a spanning tree. It's not a tree network. You have full capacity available from node to node communication. When you use the largest instances in a specific class, you get the full capacity dedicated to your instance. With the newer instances families, the C4, M4, we have the Intel chipset, which allows for things like SRIOV, which allows enhanced networking. Basically, with this enhanced networking, you're able to push a lot of packets, 1 million packets per second. The PPS is packets per second performance from instance to instance. This is a very key feature when you're looking at HPC grids, high-performance computing grids. You want to be able to push data in and out of your CPUs as fast as they can process them. The SRIO features basically allows you to reduce the hypervisor overhead. So there's no penalty of running this on the cloud. Basically, the packets are moved directly from the adapter on the host into the memory of the virtual machine. Storage is another performance factor. When you're running calculations, you want to be able to input and output data. You want to be able to input and output the data at the fastest possible speed. AWS provides many types of storage. We have internal storage, which is attached to each of the instances. So if you use an M3 class machine, you'll see that it has internal drives. Those drives are more often SSD drives, providing you with hundreds of thousands of IOPS capability to write to those drives. So they can easily be used for scratch spaces, intermediate calculations. They are temporary storage, so we don't suggest you store the data permanently on that, but they can be used for intermediate calculations on the grid. We have EBS, or Elastic Block Store, which is basically comparable to SAN storage. So you can use that, and that comes in a couple of classes. We have the general purpose class of EBS storage, which is basically based on SSD drives. We have the IOPS, provisioned IOPS class, which basically you can dial the performance you need. If you need 20,000 IOPS, you just dial the performance of the volume, saying I want 20,000 IOPS for this EBS volume. We also have the Elastic File Service, which is a shared file service. I have been asked about this quite a lot since we launched it for the shared file system requirement for many of the large grids that customers run. Basically, this is an NFS mount that mounts on all the hosts. So if you have a 1,000-node grid, a 1,000-node cluster, you can easily use Elastic File Service to mount on every one of those nodes. All the data at the back end, all the scalability at the back end is taken care of by AWS. You just need to worry about pushing data in and pulling data out from the file service. So very, very useful for shared file. One of the use cases that was missing in S3 was S3 is a very good high-performant object store, but it doesn't show up as a file system on your node. EFS shows up as a file system on your node. Obviously, we have S3, which basically is an object store, and you can put large amounts of data, and then you can hydrate that data into your grid at a very high speed in parallel. So I'll talk about that as I show the example of the architecture. Another performance factor is CPU. Again, like developers want to use the fastest CPUs. They want to benchmark their code against specific CPU types. We expose what the underlying CPU is for each of the instance classes that we provide the customers. With that information, the developers can actually benchmark and understand what time it will take for their simulation to run. How many nodes do they need for the cluster? They can size it appropriately using that information. These CPUs also provide you with advanced instruction sets, such as the AX2. Basically, developers can then use libraries for speeding up calculations. Our instances come in various T-shirt sizes. So if you're used to using AWS, this will be very familiar to you guys. For example, we have families of instances which specify what kind of workload they can run. So a C class is for high compute performance. An R class is for high memory performance. So the cost performance is the benefit that you get from every one of these families. They are optimized for a specific workload characteristics. And within the family, we have various sizes, and those sizes associate with how much memory and CPU they require. So developers can use their calculations on an instance and determine the number of instances they need, a number of cores they need to complete their simulation. This was a very important ask for us in talking to many of the financials, they wanted to use a very high-performant library which was based on CUDA GPUs. So we launched an instance earlier this year, a couple of weeks back, in fact, where we are able to provide customers with instances with up to 8 NVIDIA Tesla K80 accelerators. Each of these is capable of doing 70 teraflops of processing. That's a lot of power in one machine. They have a combined capacity of 192 gigabyte of GPU memory, so a lot of calculations can be done on this. A lot of our largest grids are being moved to the P2 class of instances. You can actually reduce the size of a grid. So if you're using 100,000 cores of regular Intel, you could reduce that number drastically by using P2 instances. So this is another performance factor. And again, P2 comes in various T-shirt sizes, extra large, 8 extra large, 16 extra large, providing you with different capacities and network bandwidth. So let's put all of this together to create a reference architecture. This is the architecture that I created for some of the banks that I work with. We have this running in many banks in various stages. Some are running them in production, some are running POCs, some are using them for dev and test. So the architecture is being used pretty much in a standard format. It's not much different from what you would already expect from HPC grid environment that you run on-prem. It's optimized in certain ways to help run on the cloud or use some of the cloud features. So for example, again, for a privacy perspective, you run the stack in the cloud. You use subnet placement groups. Now this is a very important characteristic that we provide. When you're running a grid, you want all your code or your cores or your servers to be as close as to each other to help increase the speed of inter-node communication. I mean the latency, right? So AWS has a concept of placement groups. When you launch clusters in the placement group, AWS tries its best to place these compute resources as close to each other as possible, so the latency is reduced. So when you're creating a grid, always recommended to use a placement group when you're launching the grid nodes. Again, I'll skip some of this because it's pretty standard. We use IAM for security in the cloud formation or the automation that I built. Basically, we are building all the rules and roles that are required for auto-scaling within the grid itself. So it's a fully automated environment. We define the roles. The roles are assigned to the EC2 instances. And the EC2 instances can then scale out or scale back in without any human intervention. KMS is used for encryption. For the shared file service, we use EFS. This is one of the options. If the customer needs more high performance, I'll talk to you about some other options that I've built into the CloudFormation solution. Obviously, S3 is our central data lake or storage platform. This is used for different scenarios in how you operate the grid. So if you operate the grid in a specific way, like for a transient grid, you can take the calculation data for the calculation, hydrate it from S3, and once the calculations are done, you can get rid of the grid completely and store the data back in S3. So transient grids can be created with this CloudFormation or this architecture. So if you require some high performance parallel file systems, the solution includes the flexibility to install software for parallel file systems such as Gluster or Lustre or IBM GPFS. So the automation that I've built, basically at the click of a button, will create the cluster, create the file system, the configuration of the file system, and also make it auto-scaling. So in the sense, when you launch this environment, you can specify how many terabytes of storage you need, how many nodes do you want for your metadata, how many nodes do you want for your data store. You can specify all of that, and the CloudFormation will build out all of that. You don't necessarily need to have this layer. If you're using EFS and EFS is sufficient for your grid compute, then this layer can be completely deleted. The next next part of the operations is basically making sure that you're monitoring, auditing, and logging all your information about how you're using the cloud. So we have a bunch of services that help with that. In this grid computing, we see a lot of customers do the scheduling a couple of ways. They may use their own in-house scheduler that they have built. They may use a third-party scheduler. Very popular ones being Data Synapse from TIBCO or IBM platform Symphony for Monte Carlo simulations. So the node that is there basically can be configured to run one of those schedulers. Or you can also have your application directly manage your compute resources. And finally, the compute layer. This is an auto-scaling EC2 instance layer, which basically scales off the jobs in your queue. So at the very start of this infrastructure, you can specify the minimum set of compute resources you need that you want to start with, and then you can scale out based on the number of jobs in the queue. In terms of, so that's basically the architecture. It's pretty similar to what we see in on-prem grids. This is an easy way for customers to migrate their grids to AWS. If you're already using Symphony or if you're already using Data Synapse, it just moves over. In terms of operation, we have a couple of ways to operate the grid. Like I mentioned earlier, you can use this automation to create transient grids, in which case you will have your data coming in from your corporate data center, going into an S3 bucket. From that S3 bucket, you'll establish a grid environment and do the calculations, push the data back into S3, and suck the data out from the data center back from S3. You could also have a long-running grid and have direct connect between your on-prem and AWS and pump data back in and out of those file systems, EFS or Lustre or GPFS directly. So that's another way of operating these grids, transient or long-running. So quickly, before I hand it over to Francis, how many of you have built a petabyte cluster, for example? So let's talk about cost. How many of you think it'll cost $100 million? 50 million? 200 million? So petabyte scale clusters are pretty expensive. Just imagine to get a petabyte scale on-prem, you probably have to spend hundreds of millions to build that. Let's take a scenario where we are going to build a petabyte scale cluster on AWS. This is easily achievable at the click of a button. You can have a petabyte scale. I have the cloud formation that I built. I can build a petabyte scale grid cluster in a matter of 15 minutes. It will require 1,572 M4 10 extra large instances, a lot less with the P2 instance types. You'll get 31,447 cores. Let's look at the scenarios of achieving the numbers. Like we have multiple options to sort of price this grid. You'll have something which is the core set of instances, and you'll have additional instances which are bought at spot to create the grid. And this will all match your requirements in terms of scalability. How many nodes do I need today, or how many nodes do I need for a specific calculation? So we look at two scenarios where we're going to create this grid. One is using 50% spot and 50% reserved instances. The other is going to use 75% spot and 25% reserved instances. The idea here being I want to show is how flexible it is from a cost perspective. So in the 50% scenario one, in the 50% RI and 50% spot, this works out to be 0.25 cents per hour per core in terms of grid price. That translates to about running a petabyte scale cluster for about $780 per hour. So that's a big difference from hundreds of millions of dollars worth of upfront expense versus running a petabyte scale cluster for $780 an hour. You can do a lot of damage with a petabyte scale cluster. Similarly, if we go further and use some of our other optimization features and maybe use 75% spot instead of 50%, we can reduce it to 0.2 cents. That's only $630 per hour for a petabyte scale cluster. Isn't that amazing? There are some other sessions also that you can go and look for how HPC is being used on AWS. And I would say, with a few bucks in your pocket, go and build the next petaflop cluster on AWS. Thank you.